Hey, how's it going, Hoora?
Hi, Adam. Thank you so much for inviting me, and good evening, everyone.
Yeah, thank you
Nice
for
to meet
stepping
you
up.
all.
Yeah, I think it's again super last minute. So I'm super grateful for everybody, all our presenters tonight who have put your hand up and said yes, you will be a part of it all. So
My pleasure.
ready when you are, Hoora. Yeah, if you want to jump onto your share screen there, we're ready.
Yeah, sure.
Ready to hear what you've got.
Yeah, we have a very nice weather,
It
and
is. It's absolutely peachy outside. Yeah,
mm,
I can't believe it's like 10 to 7 and it's still sunny in
yeah,
Toronto.
we
I
suddenly jump from winter to summer, I think,
really, yeah, it
without,
was. It's very sudden, very
Yeah,
sudden.
exactly.
Was walking to work this week and there were leaves on the trees. I'm like, this wasn't there weren't leafy trees like a week ago. So yeah, it definitely changed rapidly.
Exactly. So thank you so much, Adam, for inviting me, and I really enjoy, the topics that the other presenter talk about today. So, and I learn from them. So I am Hoora. I have a PhD, just a very short uh, biography from myself. I have a PhD in artificial intelligence and robotics. And right now I'm working as a manager of advanced analytic data science in BMO US PMBB. And also as a part-time job, I have two other jobs as a adjunct professor at Ryerson University, and also I'm working as a part-time faculty member at Sheridan College. And for my personal interests and my hobbies, I like hiking, traveling, and biking, and also dancing. But I didn't include, dancing here. And then I played basketball, professionally when I was at university. But after that, because I was very busy, with my job and everything, just I decrease, the number of hours that I spend, for playing basketball. So this is my email address. This one of them is Gmail address. One of them is Ryerson email address that you can contact me. And if you like, I can share my LinkedIn profile with all of you. If you have, any question or any you want to connect with me, so you can find me in the LinkedIn. So what I like to talk about today. So let me share, a video with you before going to my presentation, and then, I can show you what I'm talking about. Just, Adam, can you please confirm that you can see this video?
We certainly can.
Okay. Just look at this dog. This is a record from 2010. We have other records recently from the animals that, has some abnormal behavior before the earthquake happened. So you can see that the dog ran away. And then after that, that man understood that something is happening, and then the earthquake come. Okay, so let's go back to my presentation. We have a question here. What happened in that video? Why dogs sense that earthquake sooner than the human? This was, my question in that time when I started to work on this project. So I wanted to answer that. I want to, get some details that why some animals, has some abnormal behavior before the earthquake happened. So I did a lot of research for that, and I saw that, many animals. It depends on the type of animals that can have, different reaction to the earthquake. Some of them, even can sense the earthquake 1 month before or 1 week before the earthquake happened. But in this example that I showed you in that video, you saw that a few seconds before, or a few minutes before, the earthquake is happening, the dog understand. And, it started, he started to run away and to survive, himself. And then that question was with me to understand that what should I do and how can I, use AI to solve that question. Based on my research in that time, I found that, for example, I choose one type of animal as an example, a dog, and I understood that, it can sense a primary wave of the earthquake sooner than the human. Human cannot sense that P wave or the primary wave of the earthquake, but the human can sense only the S wave, which is very, destructive, and it's destroy, all the buildings, and you can see that motion that the human can sense that. So because of the type of receptor that human has and the type of receptor that animals have, so it's a little difference. So this difference can help the animals, to sense those waves sooner than the human. But what is the question is that what is the seismic wave, and what does, what type do I have for the seismic wave? The seismic wave, if I can, introduction for that, is a sudden movement of the material in the earth. For example, those earthquakes that we are seeing. The seismic wave can travel around the earth and can be recorded by the seismometers. And you can see that, we have earthquake signal that after each, earthquake is happening, they are recording those seismic waves, and they are, publishing after that. And, the researcher can see and use those signals in their research. But what types of seismic waves do we have? We can divide it into body wave and the surface wave. Sorry, I changed the. Okay. So I can divide it into body wave and surface wave, and there is a difference between these two. What is the body wave? So you can see that the body wave can be primary wave or secondary wave or second wave. First wave, second wave. The animal can sense this first wave that is coming sooner than the S wave, but the human only can sense, the S wave when they are seeing the shaking in their building or, something like that, and they can figure out that, okay, something is happening, and they need to go out of their building. But we have another type of waves, which is the surface wave, that can be divided into lobe wave and layerly wave. So you can see in this example that we have some background noise that nobody can sense that. This is, it's coming for with each earthquake, seismic wave that we can record from the earthquake. But you can see the arrival of the P wave and the arrival of the S wave. So there is a time interval between the P wave and the S wave. So I was thinking, and then you can see that, okay, the surface wave, which is very, destroy, very destructive, and, it can destroy many buildings, and you can see that, you can see the evidence of that. It depends on the magnitude of the earthquake. But the question is that between the P wave, the time interval between the P wave and the S wave, we have a time, if we can have, a system that can recognize the P wave, which human cannot sense that, we can have a few seconds or a few minutes. It depends on this time interval that we can have, between the primary and, the secondary wave. And then we can, for example, we can turn off something. If we can alert, our people to go to the safe, place or something like that, and we can survive many human if we can recognize and we can, build that system. So my purpose in this project was because I knew that based on my, on my data that was available for me, I understood that the animal can sense the P wave. So I should use a AI model to simulate that part of the brain of the animals that can sense the P wave. So if I go to the next page, so you can see the behavior of the P wave, and here you can see it better. It's not destroying anything. It's just, coming, but the frequency of this is different, and our receptor, the human receptor, cannot sense the P wave, but animal have that those receptors, that can help them, to understand this P wave. And if I go to the S wave, which is, the shape of that, is different. So you can see in this GIF animator, is showing, better. So you can see that the S wave is much, stronger, that can destroy, the building. It depends on the magnitude of the earthquake. So here are the examples of the, the primary and the secondary wave and the surface wave. So you can see that, can be, destroy, can destroy, the building or the earth, the surface of the earth or not. So you can see when the P wave is coming, nothing is happening for the building. But when the S wave is coming, it's destroyed. And then surface is completely destroyed, that building. So from this second that the S wave is coming, and that, you're seeing that that building is shaking, the human can sense that. But animal can sense this one. Okay. I'm passing this to go to my, model that I use. Then I did some research on the, the brain of the animals to understand that which part of the animal can sense that earthquake, P wave, and how that, the limbic system of the animal can behave and can understand the fear, and then based on that fear, it can help them, to survive of that, place, and then go out, and then, not to die. So here you can see the limbic system of the animals or the human, it doesn't matter. So it has, different parts. Each part has a responsibility in our, brain. It has hypothalamus, amygdala, hippocampus, thalamus. I will, go into the detail that what is the functionality for each part. But based on my research, that I found that we have a, AI model, which is the brain emotional learning, that has a simulation of the of this limbic system. So based on that, I choose that brain emotional learning in my as my base model, and then I work on that. The brain emotional learning is, is used very, I mean, massively, is using to solve the complex complex problems. And then in my study, in my research, I use a modified model of the brain emotional learning, first for two purposes. The first one for generating the artificial intelligence, the artificial earthquake records, which can be, exactly the same as the real earthquake. The purpose of using that model to generate the artificial records was that because we cannot have the artificial record, we cannot have a real records in many, in all areas. So I should have, so I should generate some artificial records to use as an input of my model. The other purpose, the other purpose of using the brain emotional learning in my research was that I use that model to understand the fear of the animals and to understand that what is the level of the fear of the animals. And for example, based on that, I can understand that, okay, this earthquake which is coming has a low fear. This one has a medium fear. This one has a high fear, and so on, based on my buckets and based on my levels that I created for my data. So here in this slide, you can see the different parts of the limbic system. And as I mentioned before, the emotional parts of the animal brain or human brain, it doesn't matter, has an important role for making a decision or making a response to the environment. It can be it can be any emotional reaction to the environment. It can be fear, it can be happiness, it can be, I don't know, angry or something like that. But I just focus on the fear because I was, looking into, to understand that, how that animal can fear of the earthquake, and based on that, create my intelligence model. So you can see here the different parts of the brain emotional learning. It can have a thalamus. This thalamus, the first part, can give the sensory inputs from the environment. It can be any signal from the environment. So in my research, I use the P wave as an earthquake, as a seismic wave, and I consider as the input of my network. And you can see that the thalamus is sending all the signals into the sensory cortex, and then after sensory cortex is divided or distributed to different parts. It can be go to amygdala, it can be go to the orbitofrontal. Orbitofrontal, you can see that it can receive, all the signals from the sensory cortex, and then it can process it. But the main responsibility of the orbitofrontal is controlling the amygdala for giving a relevant, response to the environment, and also it is applying the reward and the penalty on the signal that is, is receiving, and then based on that, it can control what can be the response of that stimuli or that input that the that part of the brain is receiving. And then finally, after all the processing, amygdala is responsible to make a decision, and then that decision can be fear, that decision can be happiness, or other emotional reaction to the stimuli that we can have at the beginning. So I'm passing, to, these are the formulas for, for the functionality of this brain emotional learning. And so I'm passing them. But in my model, I wanted, to improve the performance of that brain emotional learning. But how can I do that? I knew that, that if I go back to this model, we have some weight here, and we have some learning parameters that we may have in my, in our network. So my purpose was that to use optimization algorithm and to use learning automata to help me to, use first, instead of this weight that we can use to connect each part of this neural network. And then the second one is optimizing and finding the optimum value for the learning parameter that I have. So the learning automata is, I can say that is an iterative process of selecting an action randomly, and then based on that action, it can, it can give, for example, in this example, you can see that it can give a feedback from the environment, and then based on that feedback, it can do an action on that environment. But we can have different types of learning automata that I use in my, in my studies. So the first type of learning automata was finite action set learning automata, or as an abbreviation, I can use FALA. So the FALA, so it's obvious from its name, is finite action. So it means that the action should be finite and predefined. And then based on that predefined action, I can, change the probability of, the probability of my model. And then, that the environment can respond to this action by, the reinforcement signal that it can produce. The other type of this FALA can be divided into different types, which is the linear reward inaction algorithms and linear reward penalty algorithms, that I use, and I tested on my data to be sure that which one can, perform better for my, input data. I'm not sure why it's not passing. Okay. The other type of learning automata that I used in my project was pursuit algorithms. The pursuit algorithms, is using the history of the selected action, and it can, also it can use the reinforcement signals, and then based on that history and the reinforcement signal, it is changing, the probability, is updating the probability of action, and then based on that, it can recognize that what is the next best action to choose. And also, I work on the CALA, which is the continuous action set learning automata. The purpose of choosing this model, these algorithms in my project was that because I needed, to choose a learning automata that has the action, which is the which I can use to find the optimal parameter value of my model. Because as I mentioned, I had two purposes. First one, finding the optimum value of the learning parameters in my network. The other part, instead of using the weight of my, base model, which is the brain emotional learning, and then learning automata and other optimization algorithms can, act at the same formula as the weight of that network. Beside of this learning automata, sorry, I use different, strategy, which is different optimization algorithms that then nowadays you can see, we may have, we may use, in our project, which is one of them is GA, genetic algorithms. As you can see here, this is the flowchart of how I use the GA in my, project. I generated the initial population, which can be, weights or the learning rate parameters of my network randomly. And then based on that, I needed to evaluate the error of my network, which is the Bell model, as the cost function. And then based on the nature of the genetic algorithms, it is selecting some parents, and then it is generating the new population by doing the crossover or the, the mutation. And then based on that, it is generating the new new child. And then based on the new child that is producing, we can estimate or evaluate the error of the Bell model. And then this can be, repeatedly done until, my model converge to a specific level of the error that I specify, or the, I mean, the number of iteration that I consider for that. The other optimization, the algorithm that I used was PSO-based learning algorithms, the same as the genetic algorithms. Here, by the difference is, in the PSO is inspired by the social behavior of the animals, such as bird. So again, I'm initiate the particles randomly, the same as the previous one. It can be weights or learning rate parameters, and then based on that, I can find the initial particle velocity randomly, and then I will train my network for each particle, and then I will evaluate the error of my neural network as a fitness function, and then based on that, it can update the position of each particle that I created randomly at the beginning by this formula, until I reach to a point that we can say that, okay, that particle is giving me the best answer for my weight or the learning parameter, which is the optimum value of those. And the last, optimization algorithm that I used was ABC-based learning algorithms. So it's inspired by the honeybee behavior. So, but I can say that all the behavior and all the steps in these three algorithms that are, optimization algorithm that I showed you, all of them are doing the same, steps. We are initialize the population of the solution that we have. It can be weight, it can be learning rate parameters, and I will evaluate my population based on the error of my network. And we are calling it as a fitness function. And based on that error that I'm getting, I need to create a new solution based on that. And then I will repeat and I will compare and I will update that solution such a way that, I can have a better fitness function at the end, which I'm looking into very low level of the error of my network. But the question is that, can I add, the earthquake signal exactly and directly to my network? No, it is impossible, because it has a very data point and it's not useful if I can use that. So first, I needed to do some feature engineering, feature selection on my earthquake signal, and then separate that P wave and the S wave from my, from my earthquake or original earthquake signal. But how can I do that? By applying the power spectral density function, which is the PSDF. If I apply the PSDF, I can find the frequency of, of my data points. And then based on that, I can figure out that which one is related to the P wave and which one is related to the S wave. Because my purpose was that I should reach, because based on my, my studies, I understood that it's not related to the S wave. I should look into this frequency that can lead me to the P wave, because human cannot sense the P wave. Another neural network that I used, part of my brain emotional learning, was adaptive neurophosis inference system, or AMPHIS. The purpose of using AMPHIS in the amygdala, which I, which I showed the structure of my neural network, was that because after, doing the feature selection and after processing and after, understanding that what should be my weight or what should be, the optimum value for my learning parameters, I should translate it into the different levels of the fear that, can animal can sense. So based on these rules that AMPHIS can give me, I can understand that, what is the level of the animal based on the different magnitude of the earthquake. So as you can see here in the AMPHIS model, we have different layers. So you can see different layers here. Each layer has, responsibility. And for example, in the level 1, we are falsification, we are generating the membership grades, and in the layer 2, we are calling as a production. Each node in this layer is the node, and then we are multiply the incoming signals that is coming from the the previous layer. And then in the layer 3, we are doing normalization, which means that if we are using the sum, we can calculate the ratio of the that rule that should be fired and sent into the next layer. And the layer 4, because if you remember the layer 1, which is the falsification, so in the layer 4 we need to defalsification. It means that every node in this layer is a square node with the function that we have, so we are applying defalsification for those. And then in the last layer, you are seeing the output of my my input, and we can see as a final step, and we can see the different, we can create a different rule based on my input signal to that. But one of the problems that I faced in this project was that because maybe we can say that, okay, the earthquake signal is not taking that much. It's just 40 seconds or 30 seconds. So it's not that much. But when I want, when we like to analyze them or, do signal processing for that, it can give me many data points. But if I consider all those data points as the input node of my neural network, it is impossible. I cannot say it is impossible, but it is increasing the complexity of my neural network. So, I did something at the beginning. I did feature engineering and feature selection, and I applied the PSDF on that, to find those important frequency that I need for my model, but it still is not enough for my purpose, because I want to keep that neural network as simple as possible. So I use this idea that I can use the deep belief network for size reduction. It's a kind of dimensional reduction. It can help me to decrease the number of features that I need to pass into orbitofrontal and the amygdala of my model, and then based on that I can speed up the process, and I can decrease the complexity of the model. The idea of using the deep belief network in my project is that if you consider, for example, 101 as a data points of my PSDF, PSDF that I apply on my real earthquake signal. So I'm considering this network. The input layer and the output layer has the same number of nodes. So if I consider 101, for the number of nodes here, so I should have 101 number of nodes here as the output. But if I consider the hidden layer as the less number of input and output layer, and then train such a model to, until it's converged, so I can say that this number of reduced features or number of nodes can be a representative of the whole nodes at the beginning that I enter into my network. So it's a kind of extractive feature from thalamus. It's the reconstruction extractive feature from thalamus, but here I'm using the less number of nodes for my hidden layer as a reduced feature. So then the question is that maybe you ask me that, okay, how can I know that, how many numbers should I consider as a hidden layer? It's a kind of try and error, but you can use, the same way as I'm using, the optimization algorithms. You can use the optimization algorithms to, try different number of hidden layer, and then based on the performance that you are getting from this network, you can say that, okay, how many nodes I can have in the as a hidden network, as an optimum hidden network. So in my first proposed model, as you can see here, I have a feature extraction. I have a input nodes, which is the earthquake signal, and then I'm passing into the thalamus. And then here I'm doing the feature extraction, which is I'm applying the PSDF. And then the result of this analysis will be sent into the sensory cortex. In the sensory cortex, I'm applying the feature reduction, which is that deep belief network. I'm reducing the size of my, features, the number of features that I'm using. And then you can see that the output will go to the orbitofrontal, and also one version of that is going to the amygdala. But here we have, as I told, as I mentioned at the beginning, this orbitofrontal is controlling the amygdala to propose, appropriate behavior for animal or for human. So it can be, control the amygdala by applying the reward or penalty, or, it can be, other action that it can, apply on the amygdala. But here in the first proposed model, I'm using the optimization algorithm to find, the optimum weights of my network. In the second proposed, model, I'm using the Bell weight correction algorithms as is, but I'm using the optimization algorithms or learning automata to find the optimum value of the learning parameters of my network. So the same structure I'm applying, the feature selection is doing in thalamus, the deep belief network is doing in the sensory cortex, and also I'm sending the result into the orbitofrontal and amygdala. And I forgot to mention this, that I'm applying the AMPHIS model, which is which can help me to translate the results of the amygdala into the different level of the fears for the animal. So the output of this brain emotional learning is going as an input of my learning automata. And then based on that, I'm updating the probability of each action. And then again, I'm applying that action to my model. Here is the result that I received. I had to generate some artificial earthquake as the input. Also, I use the real, artificial. I use the more than 100 real earthquake signal from the very good, web page. And also for those areas that I didn't have, the earthquake signals, I generated the artificial, earthquake as by using the brain emotional learning. So you can see that, how can I generated the earthquake and how I verified that earthquake. So here in the result, as you can see here, I applied a different, optimization algorithm. It can be CLA, which is the one type of learning automata that I apply, PSO, GA, ABC, and I compared those modified version of the brain emotional learning with the original one, which is the Bell. And I saw that the Bell CLA is doing better, and is has a lowest error in my project, in my model. So in the right side, you can see the result of the first proposed model for a sample of the test data. I didn't mention that I divided in my data set into training set and the test set, and I train my model. I use the training set to train my brain emotional learning, and I use the test set to evaluate and to see that how my network is performing. So you can see here, some example I put here as the example of some famous earthquake signals. As you can see here, I know that what is the real magnitude and what is the prediction, magnitude, and what is the error in percentage of my models for different, combination of the, proposed model, which is the Bell GA, Bell ABC, PSO, and CLA, which is the CLA has the, a better response and better performance for my model. But if I go back here and I show here for the amygdala, I'm predicting the magnitude of the earthquake. So here the earthquake signal is coming, and here I'm predicting, the magnitude of the earthquake. But I'm applying the next step. I need to apply, the AMPHIS model to create those fuzzy rules, and then based on that, I can understand that what is the different level for that. So based on the data that one company provided me, we could understood that the different magnitude range, it can have a different fear level. So you can see that if the magnitude of the earthquake is between 0 to 2.2, it can have a fear level very low, and until 7.2, between 7.2 and the 8 earthquake, which is the extremely, high magnitude. So very, if we cannot, experience that much, but even the 6 as a magnitude of the earthquake is high, but we can have a different fear level, and then based on that, I can verify that how my after applying the AMPHIS model, how my model is acting. So you can see exactly the same as the previous one. Bell CALA is doing better than the other proposed model. So here is the result of the second model and the predicting of the level of the fear for 10 samples that I put here. So these events are very famous, this, famous earthquake in the world. So I knew that, what is the fear for that and what is the predicted fear that, different models, have. And then based on that, I could verify that what is the error and how can I improve the performance of my model. And in this chart, you can see the performance of different algorithms on my training set. This is for second proposed model. And then you can see that exactly Bell CALA, has the lowest error compared, to other model that I have. So I can say that, the number one Bell CALA is the top one. And then after that, Bell PSO, which is the combination of the PSO optimization and the Bell model, is doing better than the other model. For the GA and the ABC was the worst. Worst algorithms for me compared to the data that I use. And for the GA, I can say that it is very slow, so I prefer not to go with that. So I can say that CALA and the PSO is doing better than the other algorithms. Any question? I'm not sure how much time I spent. Adam? I think it's too much,
Yeah.
yes?
So look, where
Because when I
no,
start,
look,
talking, I cannot control myself.
no, look, that's fine. Like, I mean, look, we kind of say 15 to 20 minutes, but obviously, the content's fantastic. So as long as you want to
Okay,
go,
no,
we're
it's
good.
finished. Right now it's finished, but any question from the
Okay.
audience?
Vino had a question. She asked, how did you pick your topic to present tonight?
Good question. Because this project is very important for me. Why it is important? Because I had many challenges at the beginning. In that time when I started working on that project, it wasn't that much information. It's lack of the data, and I faced many challenges to provide and collect all those data that I needed for my project. So I spend, I can say that I spend many hours to just talk to different companies to get funds from them, and based on that, I could, collect those data, because it was very important for me to understand that, okay, well, how animals, can react to that specific magnitude of the earthquake. And then this is not cheap to keep the animals in a place and then record all the behavior of them, and then based on that we can recognize, because earthquake is not happening that much. So we needed to, we needed to generate artificial record, and then based on that we can, understood the level of the fear of the animals. So just because of that, I choose that topic. I thought that maybe it can be, interesting for others as well. I'm hoping.
Yeah, no, it certainly is. I think it's a fantastic topic, and provides data and dogs, which I think are both fantastic things.
Yeah, and also, I saw that the cats, the behavior of the cats before the
Hmm.
earthquake is happening, they are going up. The dog
Interesting.
is going, ran away, and they are trying, to survive themselves and go out of the building. And when I saw the video from the cat, they are going up, and for example, the fish. I can say that even a few days, because the dogs and cat, a few seconds it takes, to recognize those signals. But
Mm.
for the fish, in the area that I was living, I experienced for myself, because I saw before the very, very, high magnitude of one earthquake that I, experienced in my life. Many fishes died before, that earthquake happened, because, they have some receptor in their body that they can sense the some magnitude, because we can have, different signals from the earth, and
Mm.
then before the earthquake is happening. So the fish can recognize those signals, and then they want to come out of the water. So when they want to come out of the water, suddenly, there is no water. So because they cannot tolerate it, they cannot, be in that specific environment that can, give them, that, abnormal behavior.
Mm.
So many people saw that, the fishes are dying before the earthquake. But this is an open research area that still is that they are working. Japan, I remember Japan is keeping the fishes in an aquarium, and then
Mm.
based on that, the behavior, abnormal behavior they can understand, and they created the early alarm system, and then based on that they can text, the citizen that okay, the earthquake is coming, you need to go to a safe place, and then to survive yourself from the
Mm.
any deaths or something like that. But
Yeah, sure.
I can make a conclusion based on that
That's
we
right.
cannot.
We've got one more
Yeah,
question to jump in
yes,
before that.
yeah.
Awesome. It was a question from Marwa. Marwa said she really likes the topic. I think it has a huge impact, that being saving human life. She asked, how do you think this can be commercialized? For example, deploying it in places that have high earthquake activities, like in Asia.
Yeah, for sure it is applicable. I wanted to say exactly this one, that you cannot use only the animal reaction to the earthquake. It
Mm.
can be evidence beside of all other evidence that you may analyze and you may have, and then it can be as a predictor to help you that what is going on in the future. So but I can say that keeping the animals in a place and then just monitoring their behavior is very, very expensive. So
Mm.
if we can use the simulated brain system that can act the same way that the animal are behaving, against the earthquake, or different signals of the earthquake, it can, save many costs, I can say. Because, I experienced, that's huge amount of, cost that I had to, spend to keep that animal in a small place, and then just monitoring that behavior to understand that, okay, right now, the dog is behaving abnormal, so what is going on? Or the fish, is going, for example, imagine that the fish is like this. When the earthquake is coming, the fish is going like this.
Mm.
So if you can see, all the videos in the, YouTube channel, and it depends on the type of the animals. They can behave, differently.
Mm.
And for example, the cat is going up, or the dog is going out of the building. The fish is putting, itself like this, because, the waves that, is its body is receiving that waves,
Mm.
it cannot, tolerate that waves. So it's likes, to survive itself. So
Mm.
based on that, those behavior, we can understand that, okay, for some abnormal things, this is happening. But if we want to be sure that what is that abnormal behavior, or what is happening, we need to add some more evidence for that.